Okay, picking up again with section 24.4, we can look at the energy carried by electromagnetic waves, because electromagnetic waves, just like water waves that you see at the ocean, they carry energy along with them. And one example that might be familiar to a lot of us is a microwave oven, right? And the way it works is there's a small, up near the top, a generator of microwave waves. So those pass through. Then there's some sort of fan that distributes them or spreads them out. It may not be a visible fan that you see, but there's something to spread them out over the food. And they're somewhere in the spectrum, right, of the microwave radiation, right? So my microwave says that it's at a frequency of 2.4 times 10 to the 9 hertz, or 2,400 megahertz, I believe is what my microwave actually says. And a cool side experiment you can do, if you happen to have marshmallows lying around, I'm not sending you to go to the store in search of these, but sometime when you do, is you can fill a tray, sort of like this tray of bread. Not sure why they're microwaving bread, but that's another matter. Fill a tray with marshmallows and put it in the microwave, get rid of the rotating turntable below, but just put the marshmallows in. And as you turn on the microwave, it should heat some parts up so that they're going up and down a lot, and other parts stay unchanged. And if you measure the distance between two of the points that are going up and down a lot, or two of the points that are unchanged, that will give you the wavelength of the microwave radiation. You take that wavelength, the distance between two similar crests or troughs, take the wavelength and multiply it by your frequency that you can find on the back of your microwave, you should get the speed of light, which is remarkable. I haven't tried it yet, but I really want to, and we have some extra time on our hands, so maybe it'll happen. I'll let you know if it does. Please let me know if you try it, because I would love to hear of any experiences, good or bad, with this. So we know that they send this microwave into the food, and the way that it works is the oscillating electric fields that are super fast cause the water molecules that have a dipole moment to briefly align with the field in either direction. So the water molecules start spinning very rapidly, and it's the water inside your food that causes it to heat up when you put it in the microwave. So that's pretty nifty. But we want to look a little closer at how these electromagnetic waves can then carry energy. So a way we can quantify this is in terms of energy density, where energy density, we use a small u for it, and it's the total energy divided by the volume. So density meaning that we're dividing by volume here. And I'm just going to present the end result. You can show that the energy comes half from the electric field component, that's the E here, electric field squared times epsilon naught with a 1/2. And the other half of the energy comes from the magnetic field, which carries the other bit of it. Now, more often than not, rather than work in terms of energy density, we'd rather work in terms of intensity, which we'll see is closely related to energy density. So intensity, if we're talking about electromagnetic intensity, which is a little different than sound intensity, but is something that you might have heard about if you've learned about sound, our intensity is going to be the power divided by the area. So capital P here is power. We know that power is the rate at which energy is used. So here they've plugged in the total energy divided by time for the power. Because power is energy over time. Now, a way we could measure the total energy is if we imagine having a slab here, right? We have an electromagnetic wave coming in towards a slab. Slab has a cross-sectional area A, and the thickness of it we could describe as being the speed of light times t, times the time interval that passes through. So what we could do then is say that our total energy as it passes through is just equal to our energy density, U, what we had on the previous slide, times the volume of this shape, right? Where the volume is the area times that width or thickness of it. It's the speed of light times the time. And this is just a derivation just to get to our end result. The advantage of doing that is that notice then the areas are going to divide out and the time is going to divide out. And that gives us their electromagnetic intensity, can be calculated with the speed of light times the energy density, which is a much simpler equation. So that's really handy. Some other variations we can have with it. First, we remember with that simple equation, S equals C times U, that U we could write in terms of electric and magnetic fields. But we have this handy relationship from the previous presentation that the electric field is directly proportional to the magnetic field. And the C variable is a combination of epsilon naught and U naught. So it turns out by plugging this equation into the top one, we can either write our electromagnetic intensity purely in terms of the electric field and epsilon naught with the speed of light, or we could go the other way and write it purely in terms of the magnetic field with the speed of light and mu naught. So that is a great relationship that even though in the original equation it looks like you need both, you only actually need to know either the electric field or the magnetic field because of the fact that we know that they are so closely related to each other.